Hello, my name is Antonio Rizilva. I'm co-author of this paper, Monolith Migration Complexity Tuning Through the Application of Microservice Patterns, and this is work together with João Francisco Almeida. First of all, I'm going to give you a little bit of context in the problem we have been addressing in our research group for a while, where we look at the problem related with the migration of a monolith to a microservice architecture, the identification of which microservices, and our focus is on the complexity of the migration. So what is going to be the effort to migrate each one of the functionalities of the monolith to the microservice architecture? Why is this relevant? Because basically these functionalities execute in the monolith using ACID transactions with provide strict consistency, and so the way you program the business logic is simpler in some way. But when you move to a microservice architecture, this functionality becomes implemented into a set of distributed transactions. And these introduce several problems like eventual consistency, which even may have impact on the behavior of the functionality. So there is going to be a cost to do this migration in terms of development and in terms of adding the complexity of the system. Okay. But the complexity, not the technology complexity, but the complexity in the business logic, the impact on in the business logic. So this work is made is a work that we have done work before on this, and the first one we're going to refer just to provide some context is the an approach that does the automatic identification of what should be the microservices, giving a static analysis of the monolith code. And the emphasis here is to reduce the number of distributed transactions per functionality. Okay, so in the focus of our work. Afterwards, we have done another work where you just propose a complexity metric to measure these complexities. So we should be able to, given two decompositions, show which one is going to be more complex in terms of the migration effort, or two functionalities in same decomposition, which one will be will require more effort in terms of the migration. The work we are presenting today is leverages on top of our previous work, our previous research, and now what you are looking is that, okay, we need to migrate this functionality, and now what you need to do is to understand how we are going to implement this functionality in the microservices architecture. And basically you have the saga pattern, okay? And the saga pattern is the one that actually is proposed to deal with the lack of transactional isolation. They've defined, for instance, semantic locks, which are intermediate states, and you need to deal with these intermediate states when you use the saga pattern. For that, you have, for instance, pivot transactions. There are transactions that actually define the point where if you achieve the execution of these transactions, if the execution of the transaction succeeds, the functionality is going to succeed. The execution of the functionality is not going to roll back, but you may need to compensate if something occurs before the pivot transaction occur, and the transactions afterwards are retriable transactions. So what actually you want to do in our work? Well, what we want to do, there are two research questions. First is, what set of operations can we provide to the architect such that the functionalities can be redesigned by applying the saga pattern? So this is the first one. And the second one, if it is possible to redefine the complexity value associated with the monolith migration when there is additional information about the functionality redesign. Why? Because now we have our complexity metric that looks basically at the sequence of accesses to the main entities in the decomposition. But if now I just redesign this operation, this functionality in terms of the saga pattern, I have different concepts. And so maybe I can get some tuning in the complexity. So I can help the architect to provide him more concrete values about what should be the real complexity of migrating this functionality. To do that, we work on top of a trace associated with the functionality. This trace was collected through the static analysis using our previous work. And we look at this trace and we analyze several of these traces. We propose a set of operations that allows me to implement implement the functionality using a saga pattern. So you have a sequence change where, for instance, we just, in this case, for instance, we can define a coordinator of the saga that is going to be a microservice that coordinates the distributed transactions among several microservices, and to do that we need to change the sequence of invocations. All these operations should preserve, of course, the semantics, which means in our case should access the same domain entities to read and to write. Okay, then we have add compensating. Well, when you need to add compensating, and one real relevant operation we identify is the find coarse-grained interactions, because of object-oriented monoliths are implemented using object-oriented fine-grained local invocations. And actually you realize that when two entities are become apart into two different microservices, if there is a lot of fine-grained interactions between them, the cost is going to be very high, because you get a lot of local transactions for each one of the remote invocations. And we realize that probably you can define coarse-grained invocations. Actually, is one of the patterns for distributed systems is to define a facade for remote invocations, for instance. And the final step is to assign a transaction type to each one of the local transactions we identified. Then what you realize is that, okay, you can, with these operations, the architect can redefine its functionality, the functionality different ways. For instance, on the top, you see using a coordinator. Here is more an orchestration. But these will have different complexity costs. Because of that, we redefined our complexity, or not redefine, we define a new complexity metric, or two complexity metrics that are built on top of are leveraged on our previous complexity metric. And what we have done, we defined the functional redesign complexity that they basically measures the complexity of migrating this functionality, and the system added complexity that measures what is the impact of the migration of my functionality to the other functionalities, okay? For instance, when I write in my functional writing, I create intermediate states. Now all other functionalities that access this data may need to deal with these intermediate states and, for instance, implement compensating transactions if that is the case, okay? And we have evaluated these in the context of two systems. So we identify a set of functionalities. We define the functionality into quartile analysis in terms of their complexity. We pick each one for each group, and we apply our operations manually to identify how far could we go on the redesign of the functionalities, okay? And so the first thing we have done is just to verify that actually our work can leverage on our previous work, and see that the sum of our new two complexity metrics are equivalent to the previous one, okay? And we have done, and it's okay. We verified out, okay, so it's consistent to work on top of it. Then we did another evaluation where we count the number of type operations applied in the functionality redesign, and what is the impact on the functional redesign on the migration complexity. And we analyze and see that actually you are able to tune these, okay? And another thing, so we have here much lower, okay, it reduces the complexity after you redesign the functionality. Another thing that is interesting that we observed is that the number of operations, the coarse-grained interaction is one of the most used, which means that monoliths are implemented. So this is very useful, are implemented using object-oriented paradigm. Okay, and then we have done a deeper analysis of the variations on the complexity measures, and we see that it depends a little bit. So the percentage of reduction for each one of them varies with the functionality. And another thing is that sometimes some functionality that as an initial higher value have a higher reduction afterwards. Okay, so finally, so to the conclusions, we have. So what conclusion we have achieved with this work? So there's a set of operations for the redesign of monolith functionality into the saga pattern in the context of a decomposition. Two complexity metrics that measure the complexity of redesign functionality, and the evaluation of two monolith systems. So we can conclude that this defined coarse-grained interaction is pretty relevant. All redesigned functions have lower complexity. Functionalities that are initially more complex have more room for improvement. And the percentage of complexity reduction depends on the functional business logic. Just to finish, in terms of future work, we see that something that we realize is that these traces are very long, sometimes very complex traces, and we think that will be helpful in terms of future work that we have a recommendation tool. So now that we have the operations and now that we have the metrics, use these information to implement and define and implement a recommendation tool so that the recommend the architect what he needs to do instead of the architect look at each one of the traces, each one of the functionals and tries to apply the operations. Okay, thank you. We are open to questions.